Fits in engineering refers to the relationship between two mating parts. Let's take the example of ball bearing. Ball bearing consists of outer race, balls, inner race, and the shaft. So there are two pairs of fits in the ball bearing. One is between the shaft and the inner race, and the other fit is between the outer race and the supporting hub. Now there is no relative motion between the shaft and the inner race. Or in other words, the inner race is rotating with the shaft. Similarly, there is no relative motion between the outer race and the hub. Both outer race and the hub are stationary. Let's take another example of a plumber block. Plumber block is also used to support shafts. A plumber block consists of a bush. The shaft is rotating freely inside the bush. Here also there are two pairs of fits. One is between the bush and the shaft. The shaft is rotating with respect to the bush, and the other is between the bush and the housing. There is no relative motion between the bush and the housing. Now let's study the four pairs of fits that we have seen. The first one was the inner race and the shaft. There is no relative motion between the inner race and the shaft, and it is a force fit, which is a type of interference fit. The second one was the fit between the outer race and the hub. Here also there is no relative motion, but it is a push fit. Now we can clearly see that though there is no relative motion between the two fits, but the fits are different depending on the forces between the different pairs of mating parts. Now in the third case, the bush and the shaft is a sliding contact. The shaft can slide freely within the bush, and it is a clearance fit. And the fourth one is the fit between the housing and the bush. There is no relative motion, and it is a press fit. It will be fitted using a hydraulic or a pneumatic press, because the outer dia of the push will be bigger than the inner dia of the housing. So how do we ensure different categories of fits? So the fits basically depends on the limits of hole and shaft sizes, which in turn will depend on the functional relationship between the mating parts. Let's take a few more examples. Now this is a valve seat and a housing assembly. This valve seat and housing is generally used in case of hydraulic pumps as well as internal combustion engines. So here we can see the valve guide, and the yellowish colored, then the valve and the body. So there are two pairs of fits. The valve can slide freely up and down inside the valve guide, whereas the valve guide is press fitted to the body. So here also we can see one is a clearance fit and the other one is a interference fit. There is one more example, a shrink fit holder and a tool. Shrink fit holders are generally used in CNC's modular tooling. So here we can see the shrink fit holder with a drill bit. Now this is a example of shrink fit. Shrink fit means that the drill bit is bigger in size than the hole of the shrink fit holder. To accommodate it, the shrink fit holder is first heated, and when it is heated, there will be thermal expansion and it will expand. And the drill will then be inserted into it, then it will cool down and return to its original size, and it will result in an interference fit. So shrink fit is used generally in case of permanent joints. It will prevent slipping of the tool inside the holder. So we can see there are different types of fits based on the application. The fits can be broadly classified into three categories: clearance fit, interference fit, and transition fit. One more term that is of importance is allowance. Allowance is the dimensional difference between the maximum material limits of the mating parts. The maximum material limits means bigger the shaft, the more will be the material of the shaft. And similarly, the smaller the hole, more will be the material in the body of the hole. So maximum material limits will refer to the difference between the biggest shaft and the smallest hole. So mathematically it is equal to lower limit of size of hole minus upper limit of size of the shaft. So here we can see the shaft and holes, and the lower limit of size of hole as well as the upper limit of size of shaft is shown in the red color. And the tolerance zones of both the shaft and holes are also shown. So we can see from here that if the lower limit of size of the hole is greater than the upper limit of size of shaft, it will result in a clearance fit and the allowance will be positive. Similarly, if the lower limit of size of hole is less than the upper limit of size of shaft, the allowance will be negative. So the allowance is intentionally provided to get desired class of fit. Positive allowance will result in minimum clearance, whereas the negative allowance results in maximum interference. So let's now study the clearance fit. The clearance fit results when the lower limit of size of hole is greater than the upper limit of size of shaft. The figure here is the allowance in this case will be positive, and the figure is shown for the clearance fit. This is for the nominal model where the basic size is equal to lower limit of size of the hole. So here we can see the upper limit of size of shaft is less than the lower limit of size of the hole, which will result in minimum clearance as represented by A. And the maximum clearance is as represented by the B. The actual fit will vary between the minimum and the maximum clearance. So the minimum and maximum clearance are designed accordingly so that the parts are functioning according to their intended function smoothly. Now this is a simplified view of the clearance fit. So here we can see the tolerance interval of hole. Now there are two classes of clearance fits. For the first case, the tolerance interval is shown. In this case, the minimum clearance is greater than 0. And the second one, tolerance interval of shaft when minimum clearance is equal to 0. So there are two classes of clearance fit. In the first case, the minimum clearance is positive or the allowance is positive. And in the second case, the allowance is 0. Interference fit. Interference fit will result when the upper limit of size of hole is less than lower limit of size of shaft. And the allowance in this case is negative. So this is again for the nominal model for which the basic size is equal to the lower limit of size of the hole. So here we can see the upper limit of size of hole is less than the lower limit of size of shaft. So it will always result in interference. And because the lower limit of size of shaft is greater than the upper limit of size of hole, so to assemble this, we will always have to apply a force fit or a press fit depending on the degree of interference. So here we can see A is the maximum interference that is also equal to allowance, and allowance will be negative, and B is the minimum interference. So here again the simplified view is shown. There will again be two categories. In the first case, the tolerance interval of shaft for minimum interference equal to 0. The second case is when the minimum interference is greater than 0. Finally, the transition fit. This fit may result in either clearance or interference depending upon the actual assembly. So here we can see A is the maximum clearance, which will result when the biggest hole is assembled with the smallest shaft. And B is the maximum interference, which results when the smallest hole is assembled with the biggest shaft. But the actual assembly between the shaft and hole might result in clearance or interference depending upon the actual sizes of the shafts and holes. This is the second case of transition fit. In this case, we can see A is the maximum clearance and B is the maximum interference. Now we can see that in case of the shaft 2, the upper limit of size of shaft is greater than the upper limit of size of hole. Whereas in case 1, the lower limit of size of shaft was less than the lower limit of size of hole. And if we see the maximum clearance, we can clearly see that the maximum clearance in case of shaft 1 is greater than the maximum clearance in case of shaft 2. So these are used in different applications. So here is a simplified view. So we can see there are 3 classes of transition fits. So in the first case of the transition fit, the lower limit of size of shaft is less than the lower limit of size of the hole. In the second case, the upper limit of size of the shaft is greater than the upper limit of size of hole. Whereas in the third case, the tolerance zone of shaft will lie within the tolerance zone of the hole. So that's all for this video. Thanks for watching.